All right, here's part 2 of this Math 2414 solutions to sample exam 1, starting with problem number 15. All right, so let's take a look at this integral. Now, it might not be so obvious what to choose here, but what works perfectly is if you let u be arcsine of 2x. There really isn't any other thing it can be as far as the u. So I know most of the time you use your du ending up in the numerator or whatever, but keep in mind it can be, 1 over the radical or whatever can be your du. So anyway, we have the derivative. There's the formula for the arcsine. The derivative of 2x will be 2 over the square root of 1 minus 2x all quantity squared, which is 4x squared. So it fits perfectly except for that 2. So in other words, we just have to adjust both sides by 1/2, and so the du gives us that radical. So it's a kind of problem I've helped students with this in tutoring labs and stuff, and looks like not sure what to do, but if you can make that u choice for the arc sign there, it fits perfectly. So now your integral just becomes 1/2 u du, which is obviously an easy power rule, 1/2 u squared. So basically you have 1/4 u squared. So we have 1/4 arcsine of 2x all quantity squared plus c. So that's the key on that problem, is figuring out that choice of u. Now we're starting to introduce the hyperbolic functions from section 5.8. Maybe I could have used some parentheses around there for the labeling. So it's cosh, hyperbolic cosine of x to the 5th. In other words, maybe I could have edited it to where it looked like, trying to draw like parentheses around there, like that. That's all right. If I wanted the hyperbolic cosine to be raised to the 5th, I would have used in parentheses for the entire thing, or the 5 could have been placed above the h, cosh to the 5th of x. So this is definitely written in this form, is hyperbolic cosine of x to the 5th. So look at the formula. So hyperbolic cosine derivative is hyperbolic sine of u times u prime. Now be careful here, use this formula, don't go with your automatic trig instincts, which we need to know the basic trig derivatives. But the derivative of regular cosine is negative sine. But this one is absolutely positive. So be sure these hyperbolics that you use these rules and don't go on gut instinct. So this problem's real easy now. So the derivative of x to the 5th is 5x to the 4th times hyperbolic sine of x to the 5th. Number 17, so there you go. So that's the sign with the h there means that's being raised to the 4th. So another way you can look at this is it's sort of like taking the derivative of 8u to the 4th. So you see where, hard to write this freehand here, where the u is the hyperbolic sign. 8u to the 4th, and then there's the there's the u right there. So basically the derivative of 8u to the 4th, you'd bring the 4 down, which will make that 32. So it's 32u cubed times u prime, or du dx. So get rid of that. So you see the 4 comes down. That changes the exponent. 4 comes down. The exponent becomes 3. And then I need to tack on the derivative of hyperbolic sine, which I did not put the formula there. It's on the formula sheet. But the derivative of hyperbolic sine is hyperbolic cosine, positive. So you would just end up with 32 hyperbolic sine cubed times hyperbolic cosine. Okay, the next one is a product rule, because you have two functions of x multiplied together, x to the 4th times hyperbolic cotangent, which you see the derivative formula for that right over here, negative hyperbolic cosecant squared. So obviously you got two different orders to do the product rule. I chose f prime g plus fg prime. So the derivative of x4 is 4x cubed times the hyperbolic cotangent plus the x to the fourth, and then from right over here, of course, the u prime in this case will be 1 because that's x. So it's negative cosec squared x. So keeping the parentheses around it's fine like that. You got to have, if you have the negative right there, you have to have parentheses or that would look like subtraction. But if not, if you want to get rid of the parentheses, you can just put the negative out in front and you no longer need the parentheses. So that's, okay, so that was just a straightforward product rule. Now we have a natural log here is our primary function, but on the inside we do have a hyperbolic secant. So essentially, you see I wrote this as basically natural log of u, where u is all of that stuff inside the parentheses. So the derivative of natural log is always just du over u. So you see I just kind of wrote this in. That means it's going to be hyperbolic secant 4x plus 10, the derivative of that, over that. So we know that's going to be our denominator, the hyperbolic secant of 4x plus 10. So what we're going to do now is use the hyperbolic secant derivative formula for the numerator. So it's negative secant, hyperbolic secant, hyperbolic tangent. But then one thing you got to be careful of here is then you got to take the chain rule again. This is, I call these double chain rules. That's not really an official math term or anything, but I then also have to take the derivative of 4x plus 10. So that's where that 4 is coming from, because of the chain rule for that part right there. And then you see, just by coincidence, then these hyperbolic secants just happen to cancel. So it actually just simplifies to the negative of negative 4 hyperbolic tan 4x plus 10. Number 20 is it's not too bad. You just shouldn't be hard to figure out that you would obviously want the x to the fourth plus 10 to be your u, and therefore that derivative is 4x cubed. So obviously I didn't show the divide by 1/4, so we divide both sides by 1/4 to get x cubed dx. So the 1/4 comes to the outside. So then you're just left with 1/4 hyperbolic cosine. The antiderivative is hyperbolic sine. So there we have it. 1/4 hyperbolic sine of x to the fourth plus 10 plus c. Now this one's interesting. You have to let u be the square root of x, or x to the 1/2. Essentially, I'm using the u, it's the square root of x is in the numerator. Because actually, you see, if you look at that, it looks kind of weird, but if you just take the derivative and see what happens, then you'll notice. One thing I do in these problems, I didn't do it this time, maybe I should have, but I would have brought that square root of x up just so you could see that it was to the negative 1/2 power. So maybe I should have, I don't have a tab, I'm not working on a tablet PC right now, so I can't really draw with a stylus and my freehand, but I should have done this. I didn't put the integral sign there. Send, and then I would have put x to the 1/2. Wow, this is pretty rough looking. And then I would have brought the bottom one up like so, and made it x to negative 1/2. Well, might as well put the integral sign, or it looks bad enough. Well, all right. So what I'm saying, what I would have done is, so if you let u be x to the 1/2, you see the derivative is 1/2 x to the negative 1/2. So it does give us that radical on the bottom right here. Now it's just off by 1/2, so you have to multiply both sides by 2 to get rid of the 1/2. So actually it's 2 du, which is where the 2 is coming from, the next step. And so 2 comes out, so then it's easy. Get rid of this. I can't look at that anymore. And So then you just end up with the integral of 2 hyperbolic sine u, and that just ends up being 2 hyperbolic cosine of u, square root of x. And there we go. Now this next one's kind of interesting. It's just got a lot of busy stuff going on in there. You know, it's hard to tell. Well, I think that, you know, that hyperbolic cotangent x on the outside of this natural log part means it's probably got to be the du. Now, it's hard to tell with all this stuff, but this is, so it's almost like if, you know, if you did it wrong and then corrected it after you said, nope, this isn't going to work. So I can see this one taking, you know, more than one attempt to get the u correct. But actually the u is the ln of hyperbolic sine together. All of that's the u. Because then what happens is you take the derivative. So the derivative of natural log, of course, is du over u, which will be cosh over sinh, and that equals hyperbolic cotangent, perfect fit. Perfect fit. So this is another one where the choice of u could be a little tricky, but then it fits perfectly. So now there's nothing to adjust for, so that just ends up, all that mess right there in the integral just ends up being u du. Just do the power rule, 1/2 u squared. So it's 1/2, so I kind of put brackets or parentheses, whatever, all of that. Natural log of sinh of x, all that squared plus c. So it's kind of, yeah, it's amazing sometimes how problems that look like they could really be bad don't turn out being that bad as long as you choose the correct u and everything. Alright, I don't think this one would be too bad. The u kind of has to be the e to the 5x here, because the derivative of that's going to be 5e to the 5x. So therefore I divide both sides by 5, so that brings a fifth out in front. And then, so the antiderivative of 1/5 sinh of u will be 1/5 cosh. So it's 1/5 cosh of e to the 5x plus c. So that one's not too bad. I guess I kind of put the answer there, but looks like I didn't show any work. But I guess there really isn't a whole lot of work for this one. This is where you got to be careful. These are, now we're starting to get in the ones off those formula sheets that look like the arc one. You know, like 6 of them on the formula sheet, 3 on each side. 3 of them are arc and 3 of them are natural log. Which these natural log ones are also inverse hyperbolics, but I didn't really cover those, so don't worry about it. Well, all right, so yeah, there really isn't much here. I guess I could have written more, but it's this formula, because see, the u squared, meaning the variable goes first and the a squared goes second. So yeah, like if you reverse the 4 and the x squared here, 4 minus x squared, you're looking at arcsine. So it's that close from being arcsine, so be real careful, but it fits this formula perfectly. U is x, du is dx, so no adjustments were made. So look at the result, and then here's the answer right there. So it's u is x, so it's ln of x plus the square root of x squared minus 4. In other words, the original denominator, all in parentheses plus c. So the key on this one, like I said, is just choosing the right formula. It's easy to set up the integral here, but you got to pick the right formula. 25 is a little tricky. I already have the formula there, but you see we have I let u be the square root of 7 times x. I had to, because that way when you square it, you get 7x squared. Now notice all these formulas, you know, it's real critical whenever it's subtraction that you have the right order. But remember, addition doesn't matter. So for this particular problem, the plus, you know, a squared plus u squared is the same thing as u squared plus a squared. The order doesn't matter. So, but it does for subtraction. So you see, even though that has a squared plus u squared under the radical, that still fits this under this radical right here. So u would be square root of 7x, so du is the square root of 7 dx. So I divide by the square root of 7. And actually, I had to, well, actually, the square root of 7 is taken care of right here. Actually, looks like I did it a couple of different ways. I'm not sure what I did here. But I know I had to put the square root of 7 here to make this, oh yeah, that just comes out. Then they end up all canceling anyway. But, because so I had to force the square root of 7 top and bottom to make that part be u. Because, the x by itself is not u. It needs the square root of 7. So this square root of 7 comes outside the integral. And then I let dx just be the du over the square root of 7. Ends up canceling anyway. So, you probably could have gone about that a little bit different way than I did there, but they do end up actually going away. So we have the formula, then a would be 6 because a squared is 36, so it's negative 1 over a, negative 1 over 6, and then natural log of all that business right there. So it should be this right here. All right, how about this one? We got some e's in it. Trying to figure out what, we had a problem earlier with an e to the 2x on the denominator. Anyway, so you got to let u be e to the x, because that way the derivative of e to the x will give you the e to the x dx you have in the numerator. And then representing, so that takes care of this. But so representing the e to the 2x is no problem, because you can just write it as u squared. So then what we have here, and then of course a will be 4, if that's 16, it fits this formula perfectly. We already had that one before. And so like if 16 would have been first, e to the 2x would have been second, it would have been arcsine. So it fits this formula now perfectly. So du over u squared minus 16, so it fits this. So the u is e to the x, and then the radical part's exactly the same radical part that you're integrating in the denominator. So it's e to the 2x minus 16, and then plus c. So you get the right u, and then match the correct formula, you should be okay. How about this one? Kind of interesting, because usually when you think u squared, and I usually talk about this in class. This is in, I believe, my notes in 5.7. I believe I had one problem like this. That usually your u squared is a squared variable. Like if you have x squared under the radical, u would be x. X to the 4th, u would be x squared. But they can also be odd exponents. This is kind of a tricky looking deal to set up. I can see where that would be difficult. But if you bring that x up from the bottom to the top, that helps. And actually, if you let u be the square root of x, x to the 1/2, that's what you want, because if u is the square root of x, u squared then will be that x right there. So like I say, that seems a little odd, not what you're used to doing, but that works perfectly. Because if you let u be x to the 1/2, du then will be 1/2 x to the negative 1/2 dx. So just adjust for the 1/2 by multiplying by 2. So get that on the other side. So you have your numerator. In other words, that radical x on bottom can come up, and now that takes care of du, of course, with the 2 on the outside. The 3 is in the original problem, so I'll pull the 3 out. And then the u squared is actually x. So that's a little bit weird. But then as soon as you get this together now, okay, this goes back. This is just arcsine. This is not that other formula we're just using with u squared minus a squared. So this one's a little tricky. You got to get that u correct, and then you're in business. So now it just fits perfect arcsine. Square root of 121 is 11, so a would be 11. So it's just arcsine. 3 times 2 is 6. Arcsine of u over 11. U is the square root of x, so it's 6 arcsine square root of x over 11. And let's take a look at number 28. Find the general solution for the differential equation. It's hard to read here, but you can read it clearly on the original file. This happens a lot whenever I convert those files over to journal format that kind of messes up the printing, but the original file that you're looking at, the PDF, you can see it there, so I'm not too worried about it. Dy dx equals 2x to 2xy, so we have to separate, bring the dx up. And I don't have it quite separated because I have that y term I have to divide on both sides. Now this is saying, I usually just say solve for y, but that's what explicit if possible means. Meaning if you can solve for y without too much grief or effort, then we'll do it. And this one won't be that bad. And so you have bring the y over to dy over y, so that integral will be ln of y, and then the antiderivative of 2x dx, of course, is x squared. And then e both sides to get rid of the ln of y, so e to the ln of y will be y. Now e to the x squared plus c, if you go back and look at my notes on the 6.2, 6.3 differential equations, you'll see how I showed that always something, when you have e raised to something plus c, the c ends up being a multiple in front. So you can go back and look at that, but that's always is going to happen. So it's automatic, so you can just do that every time. So the c ends up, basically because e raised to the c is still technically a number of c. So we have y equals ce to the x squared. So that ends part 2 of this review.